Enjoyed that. So we're going to move on and try to get ourselves back on schedule so we can continue on with the rest of the day. And I'd like to introduce our next Tech Talk, which is Professor Jeremiah Blocki, also from the Computer Science Department. And I'll just turn the mic over to him in interest of time and let him go.
There we go. All right. Now everyone can hear me. All right. So thanks. I'm a new professor here in the Computer Science Department at Purdue. Excited to tell you today about memory hard functions and their application to password hashing. So as a motivating example, let's think about how passwords are stored online. So suppose that you register for an account. Here I'm registering for an account at PlayStation.com with the password 123456. Okay, that's not my actual password, but for the example, we'll go with it. So what does PlayStation store on their server? Well, as the example shows, PlayStation is going to store a record that includes my username, a salt value, and a garbled hash value. So this garbled hash value is computed using a cryptographic hash function. In this example, the SHA-1 hash function. And this hash function is applied to my password with the salt appended to it. And they'll store this random-looking string on their server. Later, if I want to authenticate, so I'll send them my username. I'll send them my password again. They're going to re-garble my password and just check to make sure that this garbled string matches what they've already stored on the server. All right. So that sounds like a nice picture, but unfortunately, data breaches occur. So sometimes due to programmer error, server misconfigurations, an attacker is able to break into the server and actually steal this cryptographic hash file. And at this point, the hacker can attempt as many guesses offline as they would like. There's no way to rate limit them. In particular, the attacker can rent time on a supercomputer. He can load a dictionary of popular password guesses, and he can just hash each password guess one after one, comparing the hash to this hash record on file. And as soon as he finds a match, he's found my password. All right. Well, the defense might seem simple. Don't allow an attacker to break in and steal this hash file. Unfortunately, that seems to be easier said than done. This is a slide that my students have affectionately begun referring to as Dr. Blocki's wall of shame. Hopefully, your organization isn't on here. But over time, this wall has grown and grown. So I used to be able to say that breaches have affected millions of users. Now we can actually claim that these breaches have affected billions of user accounts. In particular, Yahoo was breached twice a few years ago, though we only found out about it in 2016. This one breach affected over 1 billion user accounts. Similarly, the breach at Adult Friend Finder affected about 500 million accounts. The breach at LinkedIn affected over 100 million users. So these are massive, wide-scale data breaches. All right, so it's a common problem, and it's also a dangerous problem. So if you go on Amazon.com right now and search for the Antminer S9, you'll find this machine here. And here are the stats for the machine. I want to highlight one particular stat here, 14 TH per second. Now, that might seem a little bit confusing, but what the TH stands for is terahashes per second. So this machine is able to compute 14 trillion SHA-256 hashes per second. Now, this machine is intended for Bitcoin mining, but for all intents and purposes, it could be adapted to be used for password cracking as well. Now, this machine is also not terribly expensive. If you have $2,000 sitting around, you could go on Amazon right now and buy one. Further complicating this problem is the matter of password selection. Users are not known for selecting particularly strong passwords, as this word cloud might suggest. In fact, data breaches show that oftentimes the most popular password, usually it's password or 123456, or sometimes if you require numbers and letters, password 1. Oftentimes, the most popular password is used by about 1% of the population. All right, so this motivates the goal of increasing costs for the attacker. Typically, it's a good thing if a cryptographic algorithm can be executed very quickly on hardware. For password hashing, that's not such a great property. If an attacker can try 14 trillion guesses per second, he's going to crack most user accounts in a fraction of a second. So the goal is, can we actually design a function that, by design, costs a lot for the attacker to compute? So the attacker can't just sit there and enumerate through millions or billions of password guesses. Can we make this process expensive so that, searching through a large dictionary becomes economically infeasible for an attacker? All right, there are one of the classical approaches to addressing this problem is called hash iteration. And there are two popular password hash functions that take this approach, bcrypt and pbkdf2. That's password-based key derivation function. So bcrypt was used by Ashley Madison, Yahoo, and Dropbox when they got breached. And pbkdf2 was being used by LastPass when they got breached. So just as an example, what does pbkdf2 do? So LastPass was basically iterating the SHA-256 hash function 100,000 times. So instead of computing this function once, you compute this function, and then you garble the garbled result, and then you garble the garbled result again, and you repeat 100,000 times until you get some super garbled result, and that's your final string. All right, so this is 100,000 SHA-256 computations just to compute the password hash. All right, that seems like it might be useful, but unfortunately, it still doesn't put a significant dent in the problem. In particular, using stats from Bitcoin mining pools, you can estimate that the cost of computing a billion password guesses would be about $1 on customized hardware, even after they've iterated this hash function 100,000 times. All right, so this suggests a pretty major challenge, right? Over time, the cost of computing hash functions like SHA-256 have just dropped dramatically. All right, and of course, you might try to just, okay, well, let's increase the number of hash iterations over time. Well, that's not such a great solution because you have to be able to compute this function on a sequential machine. And if you increase the number of hash iterations, you're increasing delay time. So you're increasing the time that a user would need to wait to check whether authentication was successful or not. So over time, cost of SHA-256 has dropped dramatically. User patience hasn't been improving much over time. That seems to be fairly static. All right, so our goal is to develop a moderately expensive hash function. And we have two seemingly contradictory goals here. We want a function that's fast on your PC. So if you want to compute this function on your PC, you can compute it in under a second and authenticate. And we also want to have the property that even if the attacker can build customized hardware, like an application-specific integrated circuit, it's still going to be prohibitively expensive for the attacker to attempt millions or billions of password guesses. All right, that might seem like an impossible goal. But fortunately, there's one trick that we have that we can use to address this problem, and that's memory hard functions. So intuitively, a memory hard function is a function whose computation costs are dominated by memory costs. So if you think back to password-based key derivation function where we were just computing SHA-256 100,000 times, effectively we're locking up a tiny core on a circuit for a fraction of a second to do that computation. If instead we have a function whose computation requires lots and lots of memory, then we're requiring the attacker not just to lock up a tiny core on the circuit, but also we're requiring the attacker to lock up a very large block of memory. And this is expensive. So our goal here is to force the attacker to lock up large amounts of memory for the duration of his computation. And this implies that the function would be expensive even on customized hardware. You can improve, computation of SHA-256 on a customized circuit. You can't dramatically improve memory latency or memory size on a custom circuit. All right, so this is the approach taken by password hashing algorithms like scrypt. So scrypt was proposed by Percival back in 2009. Unfortunately, scrypt is also vulnerable to side channel attacks. What this means is scrypt accesses memory in a way that's dependent on the user's password. This means that if you're running a process concurrently on the same computer while scrypt is being computed, potentially that memory access pattern that you can infer is leaking sensitive information about the user's password. So this is not a great property for a password hashing algorithm to have. So that motivates the need for something called data-independent memory hard functions. And basically, a data-independent memory hard function is a memory hard function that's not vulnerable to these side channel attacks. In particular, the memory access pattern will not depend on the sensitive input, in this case, the user's password. So an attacker who learns this memory access pattern won't actually learn any information about your password. OK. So a few years ago, there was a competition called the password hashing competition. And the goal of the password hashing competition was to create the next generation password hashing algorithm. And thanks to this competition, we now have a large number of candidates. A few of the prominent ones include Catena, a candidate that received special recognition from the competition judges. There are a few variants of Catena, Dragonfly, double butterfly. We're not going to discuss the differences. Argon 2 is also a particularly notable candidate. In particular, Argon 2 won the competition. And Argon 2 is equipped with a data-independent mode called Argon 2i, which is what the authors of Argon 2 originally recommended for password hashing. They've changed their recommendations now for reasons that we'll see later in the talk. And finally, some researchers out of Stanford proposed a variant called balloon hashing, which is fairly similar to Argon 2 and Spirit with a few small differences. All right, so this motivates the question, are these memory hard functions actually secure? Do they actually, if you use these memory hard functions for password hashing, is it actually cost prohibitive for an attacker to try millions or billions of password guesses? So before we answer that question, let me formally introduce what a memory hard function is. So here we have an underlying hash function. Think of SHA-1, SHA-256, SHA-3, which in our analysis we'll model as a random oracle. And we have a directed acyclic graph, G, which encodes data dependencies. So to specify a function, all I need to do is specify an underlying hash function like SHA-3 and a graph G. And now the input to this function is password and the salt, as usual. And now each node in this graph is assigned a label. The label of the first node is just the hash of the password and the salt. And the label of an interior node is just the hash of the labels of its parents. So this directed acyclic graph tells us how different values depend on each other during computation. So in particular, to compute label 3, before you can compute label 3, you first need to know label 2 and label 1. Finally, the output of this graph is just the label of the last node. So to compute the output of the graph, you have to compute the value of this last node. To compute the value of this last node, you have to compute the value of nodes 2 and 3. And then to compute the values of nodes 3 and 2, you need to compute the value of node 1. All right, so to think about computing these functions, we can actually introduce simplifying abstraction called graph pebbling. So graph pebbling is just a game played on a graph. And in this game, you're allowed to place a pebble on the graph at time I if during the previous round you had pebbles on all of that node's parents. So initially, we have no pebbles on the graph. So that means that we can place a pebble on node 1. And in the real world, this means that we're computing label 1 and storing this data value in memory. All right, well, now that we have a pebble on node 1, we can place a pebble on node 2 because we have a pebble on its parents. So we'll place a pebble on node 2 and keep a pebble on node 1. This means that we've computed label 2, and we're storing labels 1 and 2 in memory. So we can continue this process, compute label 3, compute label 4. Eventually, we place a pebble on node 5. And at this point, we're finished. So in fact, everything I talk about from here on out is just going to be in the language of graph pebbling. But don't worry, graph pebbling is actually equivalent to computing this memory hard function. So how do we measure the cost of a pebbling? Well, we use the notion of cumulative complexity. So cumulative complexity is just the sum over time of the number of pebbles on the graph at each point in time. All right, so this is telling us how much space the attacker has to allocate and how long he has to allocate that space for. And the nice thing about this cost measure is that it amortizes. So if pebbling this graph once corresponds to checking one password guess, if you want to check 2 password guesses, you have to pebble this graph twice. And the cost of pebbling this graph twice is 2 times the cost of pebbling this graph once. So that means if the attacker wants to check 1,000 guesses, his costs are 1,000 times the cost of computing this function once. So the cumulative cost of pebbling this graph in our example is just 7. Because at the first point in time, I have 1 pebble on the graph, then 2 pebbles, and 1 pebble, then 2 pebbles, then 1 pebble. So if I sum these all up, the total cost is 7. All right, so the goal of designing a secure memory hard function essentially boils down to finding a graph with 2 desirable properties. So find a graph G with a property that has constant in degree, and the property that for any pebbling of G, the cost of this pebbling scales as n squared divided by tau for some small constant tau. Now, why do we want these properties? Well, the running time is n times delta minus 1. So if we want to actually compute this function, the running time is n times delta minus 1. So we want the property that this graph has small in degree, so that we can actually compute this function quickly on a sequential computer. We also want the cumulative cost to be as large as possible, so that we can maximize an attacker's costs. Right? We want this cost to be as large as n squared because n is the user's running time. So within a fixed running time, we want to maximize costs for the attacker. So this is the best we can hope for is quadratic cost. So if you run for 1 second, the best you can hope for is costs that scale quadratically in the number of steps. All right, and what we can show is that there's a combinatorial property on graphs called depth robustness that fully characterizes secure memory hard functions. In particular, depth robustness is necessary and sufficient for a secure memory hard function. What this means is that if your graph is not depth robust, there exists an attack on your memory hard function. And if your graph is depth robust, then we can rule out the possibility of any attack. So OK, what is this key property, depth robustness? Well, to define depth robustness, let me introduce its opposite, depth reducibility. So we say that a graph is ED reducible if there's a small subset of vertices such that by deleting these vertices, the longest path in the remaining graph is short. So here's an example of a 1-2 reducible graph. That means that we can delete 1 vertice from the graph. And after deleting this 1 vertice, the longest remaining path will have length 2. So there's a proof by inspection. Delete the node 3, and clearly any remaining path in this graph has length 2. So this graph is 1-2 reducible. Of course, if a graph is not reducible, we say that it's depth robust. So the first theorem that we've managed to prove is that depth robustness is a necessary condition for a secure memory hard function. In particular, if your memory hard function is not based on a depth robust graph, then there is an attack, and in particular, the cumulative cost of pebbling this graph is not going to be n squared. It's going to be something smaller. So in particular, if it's depth reducible and E, the number of nodes that you delete, is smaller than n, and D, the length of the longest path in the remaining graph is smaller than n, then the cost of pebbling this graph is also going to be smaller than n squared, which is what we want. So if you're an attacker, the natural question is, are existing candidates for memory hard functions actually based on depth robust DAGs? And the answer is one that's unfortunate but might make an attacker happy. The answer is a resounding no. So we looked at Catena, Argon 2, both the older version and the newest version. And in every case, these graphs are depth reducible. So in particular, Catena is depth reducible, and we can find a pebbling with cost n to the 1.62. The specific number there is not important, but notice that this is much smaller than n squared, which is the cost that we were hoping for. Similarly, balloon hashing and the older version of Argon 2i, they do a little bit better, but the cost is still n to the 1.71, which is still much smaller than n squared, the cost that we were hoping to achieve. And finally, Argon 2i, the latest version of Argon 2i, is also depth reducible. It's a little bit better than the old version, but we can still get an attack with complexity n to the 1.77. Again, much smaller than n squared, the quadratic bound that we were hoping for. And I should observe that similar results hold for most of the other known data-independent memory hard functions that have been proposed. All right, so that's perhaps a depressing picture, but the news isn't all bad. So we now actually have a way to construct secure memory hard functions. In particular, we now know that depth robustness is not only necessary for a secure memory hard function, it's also sufficient. So if your graph is ED depth robust, then we can prove that any pebbling of this graph has cost at least E times D. So if E and D are both close to n, then the cumulative cost of your pebbling is close to n squared. All right. In particular, this immediately implies that there exists a constant in degree graph with cumulative cost that scales as n squared over log n. So not perfect, but pretty close to n squared. And I should note that the best previous results, due to Alwyn and Serbanenko, achieved a bound of n squared over log to the 10 times n. Now that's nice in theory, but in practice, this log to the 10 term is astronomically large. So in practice, this bound is actually not meaningful. And finally, I'll note that we also have a matching upper bound. So in an asymptotic sense, this is actually the best you can hope for. You can hope to get a memory hard function that has complexity n squared over log n. But if you demand that your graph has constant in degree, then you really can't do any better than this. So in summary, some recommendations. Bcrypt and password-based key derivation function are no longer sufficient for password hashing. So if your organization is using either of these functions, I would highly recommend upgrading your password hashing algorithm. Argon 2i is an improvement over Bcrypt and password-based key derivation function. But as we've seen, there are still some flaws. So I should note that in the last month, the authors of Argon 2 have actually changed their recommendation. So they're no longer recommending the data-independent mode of Argon for password hashing. They're recommending a variant called Argon 2 ID. Basically, what this mode does is it runs half the time in data-independent mode, and then it switches over to data-dependent mode. So what this means is that if there are no side channel attacks, then it resists our pebbling attack because it runs in data-dependent mode for half the time. And if there are side channel attacks, then security reduces down to Argon 2i. So it kind of gets the best of both worlds, though it would still be nice to have a function that's fully data independent and has complexity close to n squared. So currently, the construction we have is theoretical, but I believe we're close to actually producing a practical candidate for a memory hard function with provable security. So look for improvements in the near future using these tools of depth robust graphs. All right, so thank you. I'll take any questions.
I have a quick question. Are the newer algorithms you talked about available in standard software libraries, or what is the status of that?
Yeah, Argon 2 is publicly available. If you search for Argon 2 just on Google, you can find their library. It's being considered for standardization by the Internet Research Task Force. So the library is public. If you want to use it, go for it. Like I said, I would recommend using Argon 2 ID because it's kind of the best of both worlds. If you can resist side channel attacks or eliminate side channel attacks, then there's no known attacks. And even if there are side channel attacks, it's at least as good as Argon 2i in that case.
Okay, Professor Blocki, thank you so much for taking time to talk to us today.